Thank you, Zucchini. Good afternoon, everybody. Thanks also to the organizer for giving me the chance to give this tutorial. So we're talking about machine learning in optical networks. The presentation is organized in two main parts. The idea is that I'm going to assume that many of you have basically no idea about machine learning. So in the first part, no idea about the methodology that are going to be used in machine learning. So in the first part, I'm going to overview some generic concepts like what is supervised, unsupervised learning, some basic algorithms. But that's not the main objective. I'm not per se a machine learning person. I'm an optical network researcher that started studying machine learning about 2 years ago. So I'll show in the second part of the presentation some applications that I did of machine learning in these 2 years. Basically, one application on QoT estimation and routing and spectrum assignment for machine learning, and one on failure management. If I have time, I'll also go through some other application from other groups. Not sure in 45 minutes I really can cover all of this. So, first question, what is machine learning? There are different definitions that can be used. There's no one well-established definition. I just picked up two. Field of study that gives computers the ability to learn without being explicitly programmed. I think this is the key point here. Whenever we do heuristics to solve optimization problems, to solve design and operation problems in our network, we are indeed telling the computer what to do with a hard-coded program. In this case, the idea is that only based on some experience, the computer learns itself how to solve the problem. And in fact, if we go to the second definition, teaching a computer to automatically learn concept, again, through data observation. So this ability of the machine to learn how to solve the problem without being explicitly said what to do comes from historical data that are used in order to understand how to solve the problem. So for our purposes, machine learning is really a set of tools, mathematical and statistical tools, that allow us to make decisions by inferring statistical properties of data that we have collected, in our case in the context of optical networks. If I use this kind of definition, there are so many other terms that really more or less can be associated with this definition: artificial intelligence, deep learning, data analytics, data mining. So it would take a lot of time to try to define the borders between these terms. In a very generic sense, I think it's nice to at least see the very high-level distinction between artificial intelligence, machine learning, deep learning. So the idea is that artificial intelligence in general is the set of all the techniques which are used in order to mimic complex intellectual tasks. Instead of having humans solving these complex intellectual tasks, artificial intelligence allows to substitute human in these tasks. But there are several subsets of artificial intelligence, as I show here. Machine learning is only one of these subsets. So there's natural language processing in order not to recognize human voice, or robotics, vision, how to recognize the content of an image. Machine learning has a specific twist in artificial intelligence, which is related to the fact that we use mathematical statistical methods to infer statistical properties of the data that we have, such that then we can make decisions based on these statistical properties. Deep learning, I guess at the end of this first part, we will understand better what it means, deep learning. So I guess machine learning started more or less in the 60s, being investigated and developed. So the first question is, why do we really get interested in machine learning in optical networks in the last 2 years? There are probably several reasons associated to that. Some of them probably they're not extremely technical, but they are related to other aspects. But if we look at the technical reason, I think there's enough to be said. First of all, dominating the complexity which is increasing in optical networks. If we consider, for example, introduction of coherent transmission, now we can choose the coding rate, we can choose the baud rate. the modulation format of transmitters. So we have several dimensions out of which we want to optimize the system. At the same time, with flexible grid, we can choose the channel spacing. So the amount of degrees of freedom of the problem of allocating resources in optical network increases. And we need to do that probably with novel technologies. Second point, this is something that has been commented by NTT recently, especially in developed countries with aging population. It's also not easy to hire skilled workforce in the field of telecommunication. So machine learning, by automating some of the tasks that traditionally were done by engineers, can help solving this problem. 5G transport, we know that, especially in the metro access part of the network, the services which are envisioned for 5G are services with very high spatial temporal dynamics. So we want to reconfigure the network according to the dynamics of the traffic. Again, if we can automate this reconfiguration process, we can deal with this problem. And finally, the enablers at the control plane. You want to run machine learning, but where into the network you will run these machine learning algorithms? Most likely you need a centralized control and management system. And nowadays we are talking about this kind of new platforms like orchestration, software-defined networking, edge computing. They're all platforms that allow to perform these machine learning algorithms in specific parts of the networks. Okay, so let's start with a categorization, a classification of the various approaches in machine learning. Supervised learning is the first family of approaches. What happens in supervised learning is that you have available from the field a set of data in which you have a connection between the features, the inputs of the problem, and the outputs that in the future you would like to predict. So for several weeks, for a certain amount of time in the past, you had this relation. So you have what is called labeled data, meaning that your input data are associated with the output that you would like to forecast in the future, to predict in the future. If your prediction goes on a continuous real value, you say that you're performing regression. If your prediction is for a categorical value, typically 0 or 1, yes or no, then you're doing what is called classification. Typical example of application of supervised learning is really traffic forecast. So for example, you have some cells in a urban environment, and then you know that at that specific time, in that specific cell, in the past several weeks, you always had that amount of traffic. So you predict for the future that more or less you will have that amount of traffic, right? So you connect two inputs, the location of the cell and the time of the day, to one output, which is how much traffic you will have at that time. It's labeled, right? It's supervised learning. But I think that there are many other examples that I could do. It's nice in an optical environment to make an example with an optical network. So imagine you have your optical physical topology, and over this physical topology you have several light paths which have been already routed. So now, which are the inputs that you want to use? The inputs might be, for example, the wavelength associated to the light path, the routing, the modulation format, and the output, meaning what you would like to predict in the future, is the bit error rate, is the quality of transmission associated to this set of inputs. So you keep collecting this information, the relation between these inputs and one specific output, which is the quality of transmission. And you hope that if you keep collecting information about this relation, in the future, when you will have a new connection requested into the network, you might be able, just by having the inputs, so the wavelength, the routing, and the modulation format, you would like to know what is the bit error rate associated to this connection. Okay? So this is an example of supervised learning in the context of optical networks. Unsupervised learning, second category class of approaches. So in unsupervised learning, you don't have this relation between the input and the output. You have a set of data. You have a set of data, and in this data, you basically try to identify which data points are similar to each other, and to some extent, which data points are different than the other data points. So what you do is basically either clustering, so aggregating the data that are similar to each other, or anomaly detection, identifying the data which somehow are outliers with respect to your categories. So again, one generic example of unsupervised learning. Imagine again you have a cellular network with different cell sites. Then only by looking at the historical data regarding the traffic, you want to classify which cells are residential cells, which cells are associated to, for example, big theaters or stadiums, so locations where you have high spikes of traffic. So what you do, you cluster the various cells in different families. There's no relation between input and outputs that you're trying to predict. It's more an attempt to do a classification of the data that you have. Let's try again to make an example in the optical networking environment. Now you have a set of, again, paths already routed into your network, and you classify them based on the quality of the signal at destination. So in this case, for example, there's one path with very good bit error rate, another path with very good bit error rate, and two paths which are associated to a not compliant bit error rate. Let's say that the threshold might be 10 to the minus 3. Here you have two light paths at 10 to the minus 2. So you start clustering the light paths that you believe are not working properly, and then you can do even some localization of the failure, right? Because if these paths, which in this case would be the paths going through this link, are the paths with a bad bit error rate, then probably the link which has the problem is the link where both the paths are going through. So you can do some localization based on this unsupervised learning. There are other two main families, which are semi-supervised learning approaches and reinforcement learning approaches. In the case of semi-supervised learning, basically you're doing a hybrid approach between supervised and semi-supervised, and here the idea is that you start by doing supervised learning because you don't have much data available, so as long as you can, you do supervised. But then when you don't have data anymore, the only way you can go is really unsupervised. So you have a blend of the two approaches. And I believe this makes a lot of sense, especially in the context of failure recovery in optical network, where some of the failures are known historically. So you do supervised learning. And some of the failures, you might not know them from the history because they never really appeared in your network. So you try to do unsupervised learning. And finally, we have reinforcement learning. Here, the concept is slightly different. The idea is that you learn by trying to take a decision. And when you take a good decision, the system reacts by giving you let's say, an award for this decision. And when you take a bad decision, you basically get a penalty. Let's make also in this case an example. So we have the usual physical topology, a path which has been routed. We have a certain condition, initial state of the path, and a certain bit error rate. And we believe this bit error rate is not satisfactory. Then we have a set of actions among which we want to choose in order to improve this bit error rate. What can we do? For example, we can increase the power, the launch power associated to this light path. And if we try to increase the power, what we see as a reaction of the system is that the bit error rate, instead of going down, it increases. There are several reasons for which this can happen, right? Associated to nonlinear impairments. Okay, so you tried it, you have a negative reward, you have a penalty out of this, so you will know in the future, under similar circumstances, that this is not a good idea to be pursued. On the other hand, if you do on the same path a change of modulation format and you decrease the modulation format, your bit error rate increases, so you get an award, you get a positive reward for this action, so you will know in the future that this is a possible way to go in order to manage it. So in the next slides, I'm not really covering much the reinforcement learning part. I'm going to concentrate on supervised and unsupervised learning. So before I move on, I'd like to concentrate on two other aspects related to machine learning methodology before going into applications. And especially, I would like to make an observation regarding what it means to do linear, non-linear prediction, because this will allow me to discuss a little bit about neural networks, which are the main tool which is used usually in machine learning. So let's start with overfitting versus underfitting, and I will start with an example that if some of you has started looking at machine learning, for sure she has gone through this example. Is the price of the houses in Portland, Oregon. It's always there in the books. And basically it says you have a set of historical data, so this is supervised learning, set of historical data which tells you for a certain size of the house what is the price. Then you have a new data point coming with a certain size of this house, and you want to know what is a good prediction for the cost of this house, for the price of this house. So what can you do? You can do actually several things. You can interpolate linearly the data that you have. But why are we doing this assumption? Why we believe that linear is a good interpolation of the data? Why don't we do quadratic, for example? Then we're going to have a solution more like this one. Or why don't we go for any other nonlinear polynomial approach like this one? So we will see that there are ways to take a good decision, but the main message that I want to give here is that it is not necessarily true that by increasing the complexity, the degree by which you interpolate this data, you improve the quality of your prediction. Okay, there's what is called underfitting, meaning you're using a complexity of your function, of your prediction function, which is too low. This is underfitting. But there is also overfitting. You're using a function which is too complex, actually, for your problem, and hence you're not having the best performance in terms of prediction. So let me go through some of the existing algorithms, and really the objective is to try to understand the main points behind the neural networks. And let's start with the most obvious example of machine learning application on data, which is linear regression that many of you probably already know. So this is exactly the same example as before. We want to find a linear, since we are in linear regression, a linear function that approximates well this data. So obviously we have infinite linear function that can be used here, right? So which one we pick? Well, a linear function is associated to some parameters, in this case theta 0, the coefficients of x1, theta 1, and the other coefficient theta 0. This is true for any linear function. So how do we choose theta 0 and theta 1 such that we have the best prediction? Very well-known problem in mathematics. You can, for example, minimize the mean square error, and you have plenty of algorithms which allow you to get theta 0 and theta 1. So, very simple and known problem. But is it always the case that you only have one input parameter out of which you want to predict your output? You might have several parameters, right? Like in the example of the light path before. You have the wavelength, you have the spectrum allocation, you have the routing, and so if you have several parameters as an input, now you are in a multivariate but still linear association between your inputs and your outputs. What if you say linear is not a good idea? Then you might have a polynomial association, as you can see here, between your inputs and your outputs. But still you're making an active decision, saying there's a polynomial relation between the input and the output. What if you have no clue about the input-output relation? What if, as it happens in many of the problems that we study, in advance you cannot really say what is the relation? In order to understand, so I can anticipate what happens. Neural networks will allow you to connect any input to any output, to generate the relation between any input and any output, between input and output in any form. But how we get to develop a neural network? In order to get there, I need another intermediate step, which is what is called logistic regression. Logistic regression is exactly linear regression, what we've seen before, but in which the output is not any value in the real domain, but is either 0 or 1. So basically, logistic regression is what I defined before classification. You have inputs, you want to decide if the output is 0 or 1, categorical. So without getting into the math of this problem, for sure, using a linear function to approximate a function that has to give as an output 0 or 1 is not a good idea. Because now a linear function goes from minus infinite to plus infinite, not really from 0 to 1. So we need a function which is simpler and goes between 0 to 1, like this one, right? And this function is what is called the sigmoid or logistic function. It's 1 divided 1 plus e to the minus c. So this function gives us the first, what is called neuron, to be used to generate a neural network. So the same algorithm that we use here through this function can be basically used under this form to connect set of inputs to a certain output. So one neuron allows us to do classification, to say if it's a 0 or 1 the output based on a set of inputs that we have by deciding that these values status. The idea is that what has been mathematically proven is that if we interconnect several neurons, not just one, several neurons, and we connect our inputs, our features to these several neurons, we can find ways such that this structure represents any connection, any function between the input and the output, without ourselves, without us saying anything about it. So leaving to the neural network the decision of which functions relates the input to the output. There's no more linear, non-linear association. There's no assumption on the connection between input and output. It's the neural network that takes this decision. Okay, so that's why neural networks are so powerful, because they allow us to generate a model between the data that we have and the answer that we want to get, which is generic and is obtained through neural networks. Now, if we, instead of using only one set of neurons, which is called the hidden layer, we use several hidden layers. The idea is that this ability of neural networks to discover the relation between inputs and outputs becomes even stronger. So to some extent, you can place in input whatever you want without pre-processing. Usually the features of your problem, they should be decided by you in an intelligent form. Now, for example, again, in the example I gave before, the features were the wavelength of the light bulb, the routing of the light bulb, the modulation format of the light bulb. So there was some intelligence in the choice of the features. The idea is that if you increase the number of hidden layers, then you just give data and input associated to your problem. And it's the neural network that, by having several hidden layers, discovers which features are more important and the relation between the feature and the output. And this is called deep learning. So the learning done through neural network with several hidden layers is what is called deep learning. That somehow promises to solve everything, because you just give data and input, you have a lot of processing, and then the output is automatically calculated by the neural. So before I move to applications, just one additional consideration, since I'm going to use these terms later. Now, let's imagine you have this data set from the field, for example, a data set of quality of transmission from your light bulbs, and you want to perform some machine learning analysis over this data. So the way you should organize your data is you reserve some of your data for the training of the algorithm, such that the algorithm develops these data values, which are the parameters of your algorithm, of your neural network, for example. You reserve some of the data to perform a test to see if the algorithm that you have developed really works, it comes out with the right solution. And then you have also a validation set. So usually it's like 60% here, 15% here, and 25% of the data here. These validation data are the data which are used if you use neural networks to decide how many hidden layers you need and how many neurons per hidden layer you need, which means basically you decide the hyperparameters of your neural network. Anyway, I'm going to use especially the term training set and test set a lot in the rest of the presentation. So what are the applications that I'm going to discuss? The applications that I investigated mostly in these 2 years. So machine learning to perform a quality of transmission estimation of unestablished light paths, and machine learning for failure identification. Let's start with quality of transmission. The motivation has been somehow already discussed. If we are dealing with deployment of new light paths into the network nowadays, we have several transmission configurations out of which we can pick the right light path transmission configuration. Now we have to choose among different paths. We can choose different spectrum allocations, different modulation formats, different baud rates, different coding rates, and so on. So in principle, for each possible of these combinations, each possibility of combining this data, we should have a prediction of how good is the quality of transmission, how good is the bit error rate at the destination associated to any combination. So what do we do today to predict what is the quality of transmission on a path before deploying the path? Basically, I have two main areas, two main approaches that we can use. We either use these exact analytical models, like those based on these split stack Fourier methods. They've been investigated quite intensively, but here the main problem is that even though they give accurate results, they're extremely heavy computationally. So in a context where you have several connections to be routed with a certain dynamicity, it doesn't really scale. Or we use, and this is what is really done most of the times nowadays, we use marginated formulas. I think the most famous one is the Gaussian noise model developed by Professor Poggiolini in the last years. So these marginated formulas are fast, are scalable, they can be used on the field in practice. The problem is that under some circumstances, they are inaccurate. They might require high margins. Why they might require high margins? Mostly because it's not, in this Gaussian noise model, you have several parameters to be given as an input. And it's not true in all the operative situations that you know the exact value of all these parameters. For example, the noise figure of some amplifier which is crossed along the network might not be perfectly known because it's not in your domain, or there is aging of the amplifier. There are several reasons for which you don't have a perfect knowledge of the parameters to be used in the model. And so at the end, the only thing you can do is to use margins at the end of your calculation, such that even if you make a mistake, still your quality is respected. The quality of transmission is respected. So the idea is, why don't we ask machine learning to learn from the past historical data points, associating the light path input features to the bit error rate of the light path, and we just leave machine learning taking the decision. On papers, this is a great idea, but there are several problems to be solved, several questions that we should solve. do we really have enough data? That's one big question. So how big the training data set should be? And are we going to get an accurate estimation of this? So we try to answer these questions in my analysis. Before I show the solution that we have proposed, let me say a couple of words on how I really see machine learning interacting with marginated formulas. I don't really see immediately machine learning to take over and work as a black box for network engineers. So imagine you have a traffic request, then you have to perform routing and spectrum assignment for this traffic request. What you do nowadays, you associate to your solution, to your routing and spectrum allocation solution, a marginated calculation of the bit error rate and destination to know if it's feasible or not, if it's a good idea or not. But as I said, these calculations usually are margin, no? They have a lot of margins to be considered. But then, at a certain point, you deploy a light path. And when you deploy the light path, you have the actual value. Right? After the deployment of the light path, you know exactly what is the real value, not the estimation. You know the real value of the bit error rate from the network. And so these values will start feeding a machine learning classifier that will start learning how the network behaves under certain input features. Right? So light paths characterized by certain wavelengths, certain modulation format on a certain path, most likely behave like that. So what I expect is that at the beginning, when this calculation gives you a value which is close to the threshold, and you don't feel safe to accept this value, then you will start getting a second opinion from machine learning. And when you start trusting your machine learning, then probably you can substitute machine learning to the marginated formulas. But at the beginning, it's really more of a joint decision process. So anyway, let's talk about how the solution whose performance we evaluated, that we investigated, works. So in our solution, we have an input, which is a set of light path features. We will see which features, and the output, which is the probability that the bit error rate is less than a certain threshold. The input features are somehow intuitive, right? The features that characterize the quality of transmission of the light path are, for example, the modulation format of the light path, the total length of the light path, the traffic volume of the light path. So what you do is you get information historically about the relations between a certain set of features of your light path and the probability that with these features you guarantee a certain bit error rate. So this is a probability, right? Because you can have several light paths with the same features that sometimes they work, sometimes they don't. So you get a certain probability. And then in the testing phase, you just get the input features, and based on this historical knowledge that you have developed, you get an estimation of your probability. The probability that the light path will respect the bit error rate threshold. So this is a simple idea to be verified. Actually, it's somehow limited in the sense that if you check the features that I consider, they're all features associated to the input light path. I don't have here any features regarding the state of the network. So a light path comes with its characteristics and I take a decision. I can do much better than this. I can, for example, add to the 6 features that I showed before, features regarding the state of the network. So for example, features regarding the interferers, the neighbors that interfere with your light path. How many neighbors do you have? How far away your neighbors are? What is the modulation format and traffic volumes of your feature of your neighbors? Okay. So you can have several features associated to your input light paths. Now that we have an idea of how to relate inputs and outputs, what are the inputs And what is the output? We need the data. And this is really a complex point to be solved, in the sense that it's very difficult to get data from the field. So what we did in this specific case, the next case you will see there are some field data. Here we just used synthetic data because we couldn't find real data. I'm not getting much into the details here. We used, for data generations, we used the Gaussian noise model associated to a specific set of features. So we used the bit error rate model associated to the Gaussian proposal from Professor Politecnico. And then we added a random noise over this basic estimation, which is negative exponential distributed under the assumption that negative exponential is the worst distribution possible. So we're going to get in our solutions a sort of worst case accuracy. Now our results will be worst case results because in terms of added noise from the distribution, the exponential negative is really the worst thing you can do. So, in other words, I'm not pretending here to say that the impact of the channel on your light path is negative exponential. I'm just saying that negative exponential is the worst case that you can have. So, the results that we will have are worst case results, which are at least a reasonable benchmark. Then we had to choose the machine learning algorithms. I talk about linear regression, logistic regression, neural networks. Which machine learning algorithm did we choose? It is not obvious to say which machine learning algorithm we have to choose to solve a problem. There are some high-level recommendations, but it's really what you learn on the field. When you do things, after a while you start learning how to pick the right machine learning algorithm. So what we did in our case was we picked all these possible algorithms, which are basically k-nearest neighbor and random forest. I haven't talked about this algorithm before, sorry, we don't have much time. And then with different parameters. And then what we did was to try them and see what was the accuracy. The accuracy is basically the probability that your prediction is correct. You want the accuracy to be 1, right? You want your prediction to be always correct. And we check the accuracy of all the approaches and the test and training time, which is basically the complexity of the approach. And we found that a good trade-off between the accuracy and the complexity was given by this random forest with 25 trees. So we have used random forest with 25 trees. Zuchin, tell me if I'm late. How 7 minutes. So we tested our algorithm on, as I said, synthetic data, specifically these two networks. This is a Japanese network, more of a small country scale, and National Science Foundation network, more a continental-wide network scale. And the first question that we wanted to answer, I mentioned it before, is how much data we need. How big the training set should be in order to give reasonable accuracy. So what I'm plotting here is what is called the area under the rock curve. It's quite complex to explain what it is. It's enough to know that the accuracy is the area below this curve. So basically you want the curve to be as much as possible close to these two axes. So the area is 1. And if the area is 0.5, that's the worst case possible. You just randomly choose. So as you can see, if I have only 10 historical data, that's what you get. But if I start having 100,000 or 90,000, then you get data accuracies which are very close to 1. So the message here is with 1,000, which is not an abnormal number in an operational scenario, you can already get pretty good results. Again, under a worst case assumption. So it's somehow suggesting that training phase might have a reasonable duration. Second question, is there an impact on the accuracy regarding the topology? And actually, yeah, there is an impact in the sense that on the NSF topology, it seems that the solution works better, which confirms intuition, because on the NSF topology, you cannot really choose many modulation formats. Right, on the NSF topology, the links are very long. Either you use QPSK, BPSK, there's not much more options. So basically the algorithm works better, because you don't have many options to choose from. So the accuracy gets higher. And here I think I can spend a little bit more time, because this is really the message, I guess one of the important messages of the presentation. So the interest in doing research in machine learning in optical networks, I don't think stays in taking machine learning algorithms as they are, apply them to our problems which have been solved with optimization before, and see if they work. They most likely will work, and they will give the same result of the previous approach, right? What is interesting is to see if whatever is out there needs to be modified in order to really solve the problem that we have in optical networks. One example, if you are on the field, most likely the data that you get from the field are data which are positive. Meaning, I don't think an operator will deploy a light path at 100 gigabit per second to discover 2 days later that the light path doesn't work, right? It's too much of an investment. So the data you get from the field are all positive samples. But can you train an algorithm if the samples are all positive? Not really. An algorithm to be trained needs positive and negative samples. So see here, if I train my algorithm only with positive samples, I have a very bad accuracy, 0.77. The solution might be, I ask the operator to deploy probes, to deploy light paths, not to carry information, but just to tell the algorithm if the algorithm works. But I don't expect the network operator to be happy to spend money to deploy light paths in order to give data to the machine learning algorithm. So this is what you get in this random approach, 0.98. If the operator is happy to spend a lot of money on probes, then you get a very high accuracy. Can we find an algorithm that tells exactly which probes you need, only few of them, not many, few of them, and get this value? Well, we tried. These selective approaches are approaches in which machine learning goes back to the user and says, why don't you make that probe? Because I really need to explore this part of the data area in which I don't have probes. So we improved the 0.77 to 0.89, but still we need to do something better. And these, I think, are the problems of machine learning application optical networks, which are interesting to us. Another thing which is often done in machine learning is to do analysis of the relevance of the features. So in my case, I had 12 features, 6 local, 6 associated to the light path, and 6 associated to the network. And so what we try to understand is which of the features are more important. What you do, you repeat your algorithm. You run your algorithm with different number of features, as you can see here, and you see if it is enough to have a low number of features to get accuracy which is very high. So this is the full case with an accuracy which is almost 1. If you start removing some of the features, you see that this case 5, which basically has only light path length, traffic volume, and modulation format, works pretty well, which is reasonable because these are really the important features that you need. So I'll use the last 2 minutes, I guess, to go through quickly soft failure identification. We know in optical network we have mostly 2 kinds of failures, hard failures and soft failures. Hard failures means one fiber gets cut and then you completely have interruption of the signal. I don't think there's much to do here with machine learning. Soft failure, something happens that degrades your bit error rate but doesn't really interrupt the network. It just degrades partly your bit error rate. Maybe there's a filter which starts getting shrinking or misaligned, So the bit error rate starts getting worse. In the soft failure management, there are several applications for machine learning. One of these is early detection. You want to use machine learning in order to get information about a failure that will arrive in the future as soon as the bit error rate starts behaving strangely, right? So in this example, you have 3 paths. Imagine you can sample the bit error rate at destination. If everything goes fine, it oscillates, but it stays well below the bit error rate threshold. Then at a certain point, something goes wrong. So the bit error rate starts increasing. So the idea is that if you can discover that something goes wrong immediately, not waiting for the bit error rate threshold to be crossed, then you can do, for example, some reconfiguration of the network, and you avoid to have downtime. So this kind of early detection is, to me, relatively simple problem which can be solved even without machine learning. We have an average, a mobile average, then you realize that things are not going well and you try to. What I find more interesting, and this is what I'm actually investigating, is to answer this question. Imagine you have 2 paths, and the 2 paths have a degradation going on due to 2 different reasons. Here maybe I have an amplifier which is not working. Here I have a filter which is shifting. Can I, just by looking at this behavior of this ramp, of this performance degradation, understand what is the cause of the failure? In other words, is there a signature of the cause of the failures associated to the behavior of the bit error rate degradation? So in this case, you really need machine learning intelligence to read this behavior and to distinguish if this behavior is due to one cause or another cause, which is what I try to say here. Cause identification, soft failure cause identification. We developed an algorithm. I know I'm pretty late at this point, so I'm not getting too much into the details. But the idea is that you monitor your bit error rate with a certain window, so you identify a certain window of data. And so you have to decide how often you have to sample your bit error rate and what is the dimension of the window. And then on that window, you perform statistical analysis, mean, minimum, max, standard deviation. In our case, since we need to find the signature of a certain cause, we even do the FFT of that window in such a way that we know a little bit the spectral components associated with that. So if we associate all these statistics to our algorithm, it ends up that we are able to have a very high accuracy over realistic data coming from a field trial. We have a very high accuracy. Let me go directly to the end. An accuracy which is almost 100%, even with window size which are not extremely big in number of bit error rate samples, and even with a sampling time which is in the order of a minute, which is a reasonable sampling time. You don't have to stay at milliseconds. Okay, if you're interested, there are several other topics, not just QT estimation and failure recovery. There are a couple of surveys online on this topic. One survey is done by me and my colleagues, and I suggest you to give a look at it. And thank you very much for your attention.
Thanks, Massimo, for the very informative talk. So, due to the time limit, we will ask all one question. So, question from.
Thanks for the talk. I noticed that you are saying the prediction accuracy is very much predict the topology, right? So, have you considered doing this kind of prediction with the dynamic topology, meaning like you may be adding? I'm assuming like if you add an amplifier or change the topology in that part of the prediction, you may need to have another trend to the model. Then that is very complex.
Yeah, I perfectly agree with what you're saying. Whatever quality of transmission application, but even failure recovery applications you want to do, they're not going to be black box solutions that work on any network. I guess they need specific training on your network, which is costly but is not unbearable in terms of cost, because the network is a big system, and having a dedicated training to me is a reasonable cost to accept. The problem is that the network also evolves, and probably you have to repeat this training, and this is what actually is an interesting question, right? We have to repeat it every 2 weeks, every month, every year. That's an interesting dimension of the problem.
Okay, I think the sector speaker again. If you have more questions,